So a few of you all asked me to make a video on this, so I'll go ahead and make it. So there's a video, right? So there's a Fourier series of a rectangular pulse. So I think so went through with you all in class. So this session is by no means to go in depth into these stuff, but it's actually signal processing. For those that don't comes, here I'll actually go deeper into what this is. But for now, all we need to know is how to go from the rectangular pulse to the Fourier series and extract the DC component and also the magnitude of the harmonics. That is really all you need to know for this course. So the first thing that we need to know is the Fourier series of our rectangular pulses is a sinc function. So it's just sinc x. So normally the version that we use, that we could actually use in the exam, is just sine of pi x on pi x. So there's the version we use here. Alright, the only thing we change it is basically what x is. So let's go to one of the questions so you can see. So forget about all this for now. Just forget about all that, right? The first thing that we need to know is the actual magnitude equation, right? So ck is, the integral, sorry, 1 on t by the integral minus t on 2 x at t by e to the minus j k omega naught t dt, right? So this is called, we call it like a synthesis equation, but it's really just an equation that's given the magnitudes of the harmonics, just to keep it simple, right? So this here is the equation that we will normally use to get everything else. So the two things, as I said before, that I need, just shaving off all the nitty-gritty stuff, we need to get C0. C0 is called a DC component, which is basically the magnitude when the frequency is equal to 0, because that is what DC is, how the frequency is 0. And the second thing is CK, which is the other harmonics. Okay, so you need to know how to get these two, and this basically is what this video gonna be about, because in the exam, yeah, he might ask you this, but if you bring a question like this, he'll either ask you to get the DC component, or he'll ask you to get the third harmonic or the fourth harmonic, or he might ask you to just get both and done, right? So that's what the video gonna be about. So I go back on top here. Okay, so the first thing that we'll derive everything from basically is the CK equation. So I'll write it over again. It would be in your best interest to memorize this equation, because I think you will want to start from here when you do any questions. Okay, 1. The DC component. So the DC component, just to keep it simple, that is C0. So K is equal to 0. If you plug K as 0 into here, you'll get this whole thing here going to go to 0. And anything to the power 0 is basically 1, right? So the equation will basically become C0 is equal to 1 on t by the integral of minus t on 2 to t on 2 x at t dt. Alright? So follow me here. So the next thing is, this 1 on t is okay, but this here, just to keep it real simple, this is basically just the area under the graph, or the area of the pulse, which is basically just the pulse width multiplied by the, I can say, amplitude here. Yeah, so let's actually go back to the question so you can see what I'm talking about. So for the same question here, so this here is your pulse. Just zoom in on that far bit, right? So if I wanted to get the area, the area here will be you're going from minus t to 0, and then from 0, so it'll basically just be 2 t1. That is the area. Yeah, that's the area. That's what the 2t1 is. It's just the area. And if I wanted, sorry, that is the width, sorry. If I wanted the area now, you multiply it by the amplitude, which is 3, because it's basically length by breadth. So you end up with your 6t1. There's the area, right? So that's the first piece that you need. So if we go back on top, this whole thing here that I was doing before, it actually have an equation for it, which you just did. So this is the area of the pulse itself. So for C0, this whole thing here is just 2. And in this case, to keep it simple, if the amplitude itself, instead of 3, it was just 1, which is what it could be. Just to keep it simple. The area of the pulse would just be 2t1, because 2t1 by the amplitude of 1 is just 2t1. So this whole equation will just become C0 is equal to 2t1 on t. Okay, so this is why you get the first equation, because 1 on t is this 1 on t here, and this area, assuming that the amplitude is 1, just to keep things simple, it will just be 2t1. So this really and truly, if you're kind of confused still, it's just 1 on t multiplied by the area under the pulse. Well, yeah. So which will just be 1 on t. And in this case, assuming that the amplitude is 1, it will just be 2t1. When you put it together, 2t1 on t. Okay, so that is where Sir got this C0 is the 2t1 on t from, right? So then he went a step further. If you actually add a different amplitude to the graph itself, all that's gonna happen is you just multiplying it by that particular amplitude. So the C0 will now become A, which is what I have amplitude to give you, by 2t1 on t. And this makes sense because this is basically this. So you have the pulse width multiplied by the amplitude. Come on, but it's still area you're looking for. So there's the amplitude, and you have your pulse width here. And it's the same equation you're using from on top here. It's just this area change because the height or the amplitude is coming, but there's the width or the pulse. And this here just you can see the height. Okay, and well, remember this t came from the Caesar equation, right? So let's try to make it real simple. So you just have a pulse, you have an amplitude, and you basically have a width, which in this case would be here from here to here, which is your width. And this area here is basically this here. If the and or the width change, the area will change. Okay, so that is the C0 component. So right, it's in the corner. All in all, the C0 is in a general form is just E multiplied by the pulse width divided by something called the period, which is what T is, capital T. I think most people know that by now. So that is the takeaway from the whole rant. So I hope the explanation was okay. So the second thing that you will need to get is something called the CKs. So you have C0, and basically I have everything else, which are the other harmonics. So the equation for this, I'll write the simplified version of it, right? So you have A, you call this the synthesis equation. It's still part of the synthesis equation, right? So A multiplied by sine, open brackets, pi k multiplied by something called d, which we'll get to just now, and all over, well, the whole thing all over, pi k. Okay, so let us break this equation down a bit. So the first thing A is just your amplitude. Amplitude is basically just the height, remember the pulse, right? The second thing, which is, well, k is just an integer, is not equal to 0. Because remember, we did the DC component already, which is when k is equal to 0. So this would be like 1 minus 1, 2. Yeah, not 0, okay? And the third thing, D. So, yeah, you see this D? The D is called duty cycle. And B is just a ratio of the on time versus the period. That's basically what a duty cycle is. Just to keep it real simple. All it is, like real people is be stressing out about it, but you don't stress too much about it because the general basic equation is basically just the pulse width. However, you want to get the pulse width is a pulse width divided by the period. And if you remember from the example we did before, the width of the pulse was 2t1. Most of the time, he will give you a pulse and you'd basically just looking for the width of it. And I think you could do a little bit of maths and figure out what the total width is. So it's just the pulse width divided by the period. And most of the time when you're doing it, it will be the 2t1 on t. Because normally it will be symmetrical about the y-axis. So it will just end up being twice. If t1 on one side, it'll be twice because it's symmetrical about the y-axis. So that is where you get this 2t1 and t. But if you notice this 2t1 and t is your duty cycle, right? But also this similar to your C0, assuming that the amplitude is 1. So the duty cycle and the DC component similar, but don't mix it up. It's not the same thing, okay? Because the C0 takes into consideration the amplitude. The duty cycle does not, okay? So what we learn, duty cycle, which is D here, is the pulse width divided by the period. Let's keep that real simple. Alright, just keep it real simple. Yeah, I don't stress too much about it. Because the pulse width divided by the period. So if you go down to one of the questions, now you look at this. So first thing we need to get is C0. So if you notice C0, there's two T1 and T. This is basically just your pulse width all divided by a period. Remember, I told you all that before. Right? So in this case, we just bring back the 3 because it's have actual amplitude. So in this case, you have to multiply it by the amplitude. Okay? Because that's ratios. So pulse width, forget what this 2t1 thing, like you actually look at it and see. So when you look at the graph, obviously it's symmetrical. So you're looking for this here. So you're going from minus t to 0, which is 1t, and from 0 to t1, which is 2t1, the pulse width. So you end up with 2t1 on top, and the period obviously is t. And you multiply it by your amplitude. So in this question here, this, remember this is your duty cycle. Okay? A is union, so that does make it the C0. But this is the duty cycle. So watch how everything that's gonna come together. C0 will basically just be a duty cycle multiplied by the amplitude of whatever they give you. That's literally all it is. So look how easy it is become to get the C0. So if they give you a duty cycle at 25%, that's basically a quarter. I think we could use fractions, right? If not, you could just use 0.25 if you want to. And the amplitude is 3. So therefore, C0 in this case will basically be 0.25 multiplied by 3, which is 0.75. Easy like that. So that's all it is. So let's recap it again. C0 is basically your duty cycle multiplied by your amplitude. Forget about this 2T1 and thing that make that confusing. All that is just the pulse width. Obviously, you can't use this one because you don't have enough information, right? So most of the time it will be centered and symmetrical about the y-axis. So that's easier. Okay, so nice. So this CK is basically what you will use to get everything else. And it's very easy now because remember D is a duty cycle. So all you're going to do is derive a general equation and just change the value of K in a calculator. So CK now will basically be, if the duty cycle was, like we say the duty cycle was 30%. Just to keep it simple, right? You can pick anything from 0 to 100%. Or to 100% being just the whole period. So you have A, which could be anything, sine pi k, at duty cycle, I don't know why you will I say 0.35. Let me remove that dot because they might think that is more. So, alright, and you're dividing that by pi k. So there's the general equation. So if you're doing an actual question, you obviously will know the value of A, and k is basically a harmonic. So if I say the third harmonic, k is 3. Plug 3 inside there, put it in a calculator, well, assuming you know the value of A, and that's basically the answer. Alright, and you just rinse and repeat it for everything else. So in this case, what is the third harmonic? So let's print it off. So in this case, C3, we know the amplitude is 3. It will be sine, open brackets, pi, k. The duty cycle they gave was 25, so it will be 0.25, put it in a bracket, yes. And you're dividing it by pi k. So in this case, since k is 3, you just write k as 3. Okay, and then, well, close your brackets up here to keep it neat. I want to actually, I could try it on a calculator and see. So 3 multiplied by, you have sine 3 pi by 0.25 divided by 3. And you get your answer 0.225 as the amplitude. So for this question, C3 was that, and C0, which is A by a duty cycle, A is 3, and the duty cycle was 0.25. So you basically end up with C0 being 0.75. So that's the recap. That's to bring everything together to make it simple. So any question, so there's the recap. Sorry for the length of the video, but I hope it was kind of clear. So in the question, they will give you a rectangular pulse. From the pulse, you'll get the pulse width, and you will get the amplitude, which is the height, the flat line value on top. Well, okay. So from these two things here, the first thing you need to get, so you have your Fourier coefficients. So the first thing is C0. C0 is your amplitude by duty cycle. Real simple, right? And then the CK is basically amplitude. Instead of duty cycle now, you're multiplying it by sine of pi k by that same duty cycle divided by pi k. That is all you need to know. So any question they might have is the DC, that is C0. I remember a duty cycle is just your on time divided by a period, which is just a fraction. If they give you, well, what percentage they give you, that's converted to a decimal. So that is what it is.